So we had this equation, the Schrodinger equation. So one thing about this wave function psi of xt that is important for you to understand, for me to understand, is that this wave function representing the quantum particle is a complex quantity. It's a complex quantity. That is, this psi belongs to complex quantity. This is the sign for symbol for complex. We have complex number is represented by complex number, field is represented by this, real number by this, any field by this. So we use this notation, that is the international notation. You can also simply use this term also. That's just a simple concept. Yeah, so it belongs to the complex, it's a complex quantity. So this wave function, to be a complex quantity is a necessity that arises from this wave equation. To satisfy this wave equation, the psi must be a complex quantity. Because if psi is real, if psi is real, then this term, as it has no iota the imaginary number, so this psi being real, this term will be real, so the right hand side will be a real quantity. But on the left hand side we see that psi is a real quantity, so derivative of psi with respect to t will also be a real quantity. So this is multiplied by iota, the imaginary number. So this term becomes, the left hand side becomes an imaginary quantity. So this being the real, this being the imaginary, so to find the solution of this wave equation becomes impossible. So for the wave function to be real, then for the wave function to be real, it is not impossible to find the wave equation as we have the one side real and other side imaginary, so it is impossible to calculate the solution, find the solution. So it is imaginary, then it is only imaginary, then this will be imaginary, this will be real. So wave function is needed to be a complex quantity to satisfy the mathematics. If equation is satisfied, mathematics is satisfied, and this equation predicts the various properties of the hydrogen atom energy states and other physical phenomena through experimentally. So this equation is right, and mathematics is also right. So we cannot challenge this equation and its solution to be complex. Now, first thing that this equation tells us, and let me just write it like you need to understand like this thing more efficiently. Let me just write this as remarks. Yeah. So first thing that we observe from this equation, that it is a first order differential equation. Differential equation in time. You can see that the time derivative of the wave function is a one-dimensional, is a linear. The derivative is of order 1. So this is the first order differential equation. Although you have the second derivative and here also, and you may also have the other derivatives, like not only the second, some other quantities also, that will be depending upon the wave function. The derivative may be of other orders also. If we consider the wave function in more than 4 dimension, that is high dimensional physics, so you have different approach derivatives also here, there, and so but the derivative of time in this equation is of order 1. So this is a first order differential equation. What does it tells us? That it gives us the time evolution of the wave function, that how the wave function will be if the wave function is at time t is equal to t naught is equal, it looks like this. Let me just write it again. Yeah, at what does this equation tells us? That if the wave function at time t is equal to t naught looks like this, then this equation tells us that we can also find the state of that wave function, that how would it look at other times. T is equal to t1, it may look like this. So t is equal to t2 or anything depending upon time. We have not considered this term. I'm just telling you the meaning of this term. So this term gives the time evolution of the wave function, that if you know the wave function, the state of the particle at a given time, then you can determine the wave function at all the times, not this in the future events like in 1 minute, 1 hour, or 1 day or year. You can find the state of that wave function. So if psi x t naught determines psi at all times. So if you know the psi t naught, then you will can also find the psi at all the times. So this is the first thing. Second thing that is important, that this Schrodinger equation is linear equation. That is, what it means by linearity, it means that if we have two solutions, that is two wave functions, psi1 and psi2, then by linearity property, a1 psi1 plus a2 psi2 is also a solution. This is also a solution of that Schrodinger equation. This is the linearity property, where these a1, a2 are complex quantities. These should be the complex quantities. These are the constants. So now these two properties are very important, that this Schrodinger equation is a first order in time, and it is a linear equation, that all the terms are linearly varying. So this is very important, that the linearity property that we will also find in MSc, that from the mathematical basis of this quantum mechanics in MSc in Punjab University starts from the linearity property, and this comes for the simple understanding of the wave function. So not in only one dimension, in 3 dimension also you have a vector, that is a vector, or any function, that is function is varying with respect to other coordinates. The vector also varies with respect to other coordinates. So if you have a vector in 3 dimensions, then you will also have the linearity property there satisfied there. So it is just a mathematical concept of linearity property, and it is satisfied by the wave function also, and satisfied by the quantum particles also. We are studying the quantum particles, so the linear motion of the quantum particles, so the linearity property. Now the things that you need to understand is that of the complex numbers, you might not understand the complex numbers even in electricity and magnetism. the equations of electric field and electromagnetic field are complex, but we take only the real part of electric field in the term. So we consider only the real part of the electric field, and the rest of the imaginary numbers are said to have no physical meaning, but not in case of Schrodinger equation. You cannot say that I only take the real value of this equation and it will not, this, if you take only the real value, it will not describe the wave function completely. So you have to take it the complex thing, complex quantity there. So first of all, the complex numbers importance here, and secondly, the complex number is represented by z is equal to a plus iota b, where a, b are real, and its conjugate is complex conjugate is z star. Z conjugate, we I pronounce it as z conjugate is equal to a minus iota b. That is, iota changes to minus iota, so it is called as the complex conjugate. Now this introduction is very important as it gives the length of complex number, which is represented by z modulus is equal to under root of a the square plus b the square, and you can see that both are real, so this is a real quantity. This is z the conjugate. You can easily check this out. If you multiply this by this, you will get a the square plus b the square. So this term, the length of the complex number, is a real quantity. When the complex number and the complex conjugate are multiplied and the square root of these multiplication is taken, we get the real number. So this is very important in Schrodinger equation, as you can see that psi in Schrodinger equation is a complex quantity. Therefore, it has imaginary part also, so there is no physical meaning of this psi. That is quite an absurd to human notion, but we can simply understand that. I'll tell you about that when we come to that. So, but the physical meaning of the psi comes when you understand about, when you put the concept of probability density, represented by P xt for one dimensional, or rho xt. So this is the probability density, and what it is equal to? It is equal to psi the conjugate of psi, that is a complex number conjugate, so complex function conjugate, into psi. So this becomes the real number, so it gives the value of the position of the particle, in the wave function, and what it describes is, it is called as the probability density, that you understand. So if you take pxt, that is probability density, that is the probability of the particle per unit length, in as we are discussing only the one dimension, and multiplied by dx is the unit of length. So this gives us the probability of finding the particle probability density, particle number partition of the particle per unit length into the length, so we get the probability to find the particle in the interval x comma x plus dx. So in this interval, that is, difference is only dx. So in this region where the particle is present, it can be found by this equation at any time t. So this is the thing where the concept of physical significance of the psi comes. That is, the if you have this wave function, then suppose the probability density of the particle is shown by this graph. So the position here, this position is the probability that the particle is maximum present. The probability that the particle should be here is maximum. That particle is at the center of the wave function. That is the wave function. The particle is at the central region of the wave function. The probability that the particle is here is maximum. Particle can be here also, but the probability that the particle is most likely to be here is given by this graph, and this is graph comes from the probability density, so it gives the position of the particle, the probability of finding the particle. So we consider that the particle is mostly present here. So that's just a simple concept that it gives the physical significance of the wave function. For example, if you take this probability density, which is equal to psi xt, the modulus the square. Of course, you know that psi xt modulus the square is equal to psi xt conjugate into psi xt. So this is the both terms are equal. So this multiplied by probability density multiplied by dx. If you take the integral, not only that this is small region, not only if you want to find the particle in this small region, if you want to find it in the space from minus infinity to infinity, like in space, like where are you are sitting, not only the small region, if you want to find where the particle is present in the whole space, from not only in 100 meters, not in 1 kilometer, in whole space from minus infinity to infinity, what is the probability that the particle is present in that region? The probability of is maximum value of probability is 1, minimum value is 0, as you know that. When taking the integral from minus infinity to plus infinity, the particle is, of course the particle is present there, then this probability is equal to 1 for all time. That particle, if you take the whole of the universe, the particle is definitely present. Not definitely, in quantum mechanics we cannot actually use the word definite. We can say that most probably the particle should be present here. That's the right way to define the position of the particle in quantum mechanics. So first of all, these terms and this Schrödinger equation, its linearity property, first order equation in differential equation, the complex number and its length importance, and the wave function is complex, so its complex nature gives a physical, is the length of this complex number when applied to the wave function. As wave function when is scared, modulus of wave function is the probability density is taken, it gives a physical significance, so this term is important. So from this equation, let me just, from this equation, let me just, write it down like this. From this equation, as dx has the units of length and the product of dx and psi xt, the modulus the square, is equal to 1, then this implies that this quantity should have the units of 1 by length. As every equation in physics should be dimensionally correct, that is, on left hand side and right hand side, the dimensions of the physical quantities, the units and dimensions of the physical quantities should be equivalent, so should be equal. So from here we see that the psi xt modulus the square has the units of length, therefore the psi xt should have the units of psi should be, units are represented by this square brackets and the physical quantity in the square bracket. The unit of this physical quantity psi is equal to, representing the quantum particle, should be equal to 1 divided by under root of L. Yeah, under root of L, where L represents the length. So if you take meter, centimeter, nanometer, micrometer, nanometer, or the femtometer, that is actually at the quantum level. So you have the units of length as 1 by root of L. But there is also another notation which is more simpler and easy to understand. That is given by Dirac in the early 1920s or 30s. He gave another method or notation for wave function analysis and Schrodinger equation to find the properties of that wave function. So this we will discuss in first semester of MSc Physics from Punjab University. So this we will understand from in the first semester. So we will get to that, but first of all we need to understand the mathematics that is needed for this Dirac's notation and other character notation. So we will get to that.